Today, I'm going to be completing Part A of Homework 1 for Process Dynamics and Controls. To begin, we are going to look at a simplified model of a single gravitationally drained tank with an area of A at the top, an input volumetric flow rate of Q in, a drainage hole of area A naught, output volumetric flow rate of Q out, and a height of H. All right. From here, we're going to look at the overall material balance, which is going to be the change in the volume of the tank over time, dAH dt equals volumetric flow rate in minus the volumetric flow rate out. All right, so how are we going to make this expression useful? We are going to look at the Bernoulli equation. The full equation goes P2 minus P1 over the density plus the gravitational constant times Z2 minus Z1 plus the initial velocity squared minus final velocity squared over 2. This whole expression equals your viscous losses. All right, so how are we going to simplify this equation into terms that we can actually use in our overall material balance? Well, if we call this area 1 and this area 2, we can see that the pressure is the same at both these points, eliminating our first term. From here, we can also compare the area at the top to the area of the drainage hole. Being that the area of the drainage hole is so much smaller, we can assume that V1 is proportionally so much smaller than V2 that we can entirely eliminate V1. And the last part of this equation we're going to remove is the viscous losses. We can assume that there are no viscous losses here. All right, so what does this give us? This gives us gravitational constant times Z2 minus Z1 equals minus the velocity out squared over 2. All right, what are we going to do with this? We want to solve for V2 because from V2 we can get an expression for our outlet volumetric flow. So if we rearrange this a little bit, we can get V2 equals the square root 2 times the gravitational constant times the height. Now where do we get the height? If we look at Z1 or Z2 minus Z1, we call these 2 points Z1 and Z2. We can call Z2 minus Z1 the height. Now from here, to get our volumetric flow rate out, we multiply the area of the drainage hole, A naught, times V2. And if we sub in our equation here for V2, we get Q out equals A naught times the square root of 2GH. Now, we can sub in this Q out into our overall material balance here, which gives us dAH over dt equals Qn minus area out times the square root of 2GH. Alrighty. And if we move our area over to here, we can get a useful differential equation of dH dt equals Qn, not Qn, 1 over A times Qn minus AO times 2G H to the 1 half. And this right here is our governing equation for our single gravity drain tank. Now, let's move on to the actual problem at hand, our 3 gravity drain tanks. Alright, so here's our actual problem. We've got 3 gravity drain tanks in series at an initial steady state. At this initial steady state, the flow rate is 1 meters cubed per second, the area at the top of the tanks is 1 meter squared, and the area at the drainage hole is 0.1 meters squared. Now what are we going to do with this? We are going to use a proportional only controller to manipulate the flow rate, and from this we're going to simulate the response of the liquid levels in all 3 of these tanks based on a set point for the third height that's 20% higher than the initial height that we're going to derive now. Now, to find this initial height in tank 3, we're going to need to use the equation previously derived for just a single gravity drain tank. What we're going to do with it is we're going to set dH dt to 0, as we're starting at an initial state, dH is not changing. And we're going to sub the Qn provided here at the initial steady state in for Qn up here. So let's go ahead. It gives us 0 equals 1 over A times Qn at our initial steady state minus the area of the drainage hole times the square root 2 times the gravitational constant times h naught to the 1 half. Now I'm calling this h naught because it's our initial height in tank 3. Now, if we move this around a little bit, we can get rid of our a here and find that h naught equals our initial volumetric flow rate over the area of the drainage hole squared over 2 times the gravitational constant. Now this is going to be very important for us for once we get into Python, we start to actually simulate our heights. We're going to need this later on. Now, what we're also going to need is our proportional gain for our controller. How do we set that up? So we're going to say Qn equals our initial steady state Qn plus our proportional gain times our error. Now what's our error? Our error is the height at the set point minus the actual height 3. This is also going to be very important for when we get into the simulation step. Now I think here we have all of the base equations that we're going to need to simulate this in Python. So why don't we move on and start doing some coding. All right, I'm going to go ahead and get started with the coding portion of our video where we are going to simulate our 3 gravity drain tanks. And then eventually we're going to try to find the ultimate controller gain. So we're going to get started by defining our variables, of course. A equals 1 meter squared. AH equals 0.1 meter squared. G equals 9.8 meters per second squared. And then we're going to have our initial volumetric flow rate, which is 1 meter cubed per second. And then from there, we're going to define our H naught, which is a function of the area of the drainage hole and the initial flow rate. So it's going to be Q in naught over AH squared, all divided by G times 2. And then from there, we can get our set point, which is 1.2 times H naught. After this, we can put down our controller gain, which for now we'll arbitrarily call 0.675. All right. After that, we've got to get our t-plot down, our independent variable, so we can eventually solve our IVP. So we're going to say our t end will be 100 seconds. And then we're going to create our t-plot using np.linspace, going from 0 to t end, and we'll stick 100 variables in there. Why not? With our variables defined, we can go ahead and move on to defining the right-hand side of our equation. But before that we do that, I'm going to go ahead and define alpha as area of the hole times np dot square root of 2 times g, because we'll have to use this expression a lot. So starting out with it and then later putting it into our definition of our right-hand side will save us a lot of time. So from here, we are going to define our right-hand side as a function of t and a vector. Eventually, what's going to be in this vector is going to be our height values. So we're going to go ahead and get to that. So we're going to call h1, h2, and h3 equal vector. And then q1, q2, and q3 are going to be a function of that height. So we're going to call np dot square root h1 times alpha q1, and then we're going to do the same with the rest of the q's. So np dot square root h2 times alpha, and np dot square root h3 times alpha. Fantastic. And then from here, of course, we are going to define our error as the h set point minus h3. And from there, we can get our q in, which is, of course, q in naught plus our controller gain times our error. From here, we're going to want to return our q in minus q1 over a. Over a. And then our q1 minus q2 over a. And then finally, our q2 minus our q3 over a. And that is all good. And then from here, we can go ahead and solve our IVP. So we're going to define the result as solve IVP with our dependent variable, our right-hand side, and then our independent variable, which is going to be the time from 0 to t end. And then we're going to want to do an np.full to create an array of initial values, and those initial values are going to be h naught. And then our method is going to be the rat out method. And finally, we want dense output, as the output is continuous. Fantastic. And then we're going to have hplot equal res.sol for tplot. And then h1, hplot1, hplot2, and hplot3 are going to equal hplot. All right, that's all good, and now we can make our plot, get our pay. So we are going to do figure equals make subplots. Then we're going to do figure dot add scatter. X equals tplot, y equals hplot1, 1. Mode equals lines. And name equals h1. We're going to do this for all of our height plots. But I am going to do it the quick way. I'm just going to copy and paste this a couple times, changing the name to h2, h3, respectively. Alrighty, and then finally we're going to do figure dot update layout. And we'll go ahead and do a width of 600, a height of 400, and we'll do our template as probably dark. Shift enter. Let's see if it works. All right. So as you can see here, we are getting oscillations for our ultimate gain. We can try to increase to 0.9 and run the program again. And we're starting to see a little bit of divergence there. What happens if we put it at 1? And here you can see we've got true divergence. So it seems like the ultimate gain is somewhere on the magnitude of around 1. And I think that is all for this homework.